This narrated PowerPoint reviews two related formulas that have to deal with frequency, wavelengths, and energy. So a typical question might read, what is the frequency of the 21 centimeter radio line? Compare its energy to ultraviolet light. Frequency is 10 to the 15th. We're going to need two separate formulas to answer both parts of this question. In the first part, it relates frequency and wavelength. The 21 centimeters is the wavelength, which is given. You have to solve for the frequency, which you don't know. The only formula that relates wavelength and frequency is right here, where c is, of course, the speed of light, which is given right next to it. So now we've identified the formula that we're going to use for the first part of the problem. So we're given that the wavelength is 21 centimeters, and we know that the speed of light is the frequency times the wavelength. So what we're going to do is we're going to try to find the frequency by itself. So we have to divide both sides of the equation by wavelength. If we divide both sides of the equation by wavelength, what's going to happen? Well, on the right-hand side, the wavelength is going to cancel. And so now we have the speed of light divided by the wavelength equals the frequency. Notice that in the problem, we are given a wavelength of 21 centimeters, but the speed of light is given to you in either meters per second or kilometers per second, not given to you in centimeters per second. So we're going to have to do a unit conversion. So we know from the formula sheet that 100 centimeters is 1 meter. So that is the conversion factor that we're going to use. And so I have 21 centimeters. I know that 100 centimeters is equivalent to 1 meter. You notice that I set it up here with the centimeters on the bottom so that they will cancel, and my answer will indeed end up in meters. So 21 divided by 100 is 0.21. So this is the wavelength, which goes in the denominator. In the numerator, we have the speed of light given in meters per second so that the meters will cancel. And so the frequency will be in the unit of 1 per second. 1 over second is the same as hertz. So if I divide these two numbers in my calculator, I end up with 1.43 times 10 to the 9th, 1 over seconds, or 1.43 times 10 to the 9th hertz. To do the second part of the problem, to compare the energy of this radio wave to energy of ultraviolet light, I need Planck's law. Planck's law is right over here, which says that the greater the frequency, the greater the energy, or the ratio of the energy of one kind of light to the energy of a second kind of light is equal to the ratio of the frequency of the first kind of light to the second kind of light. So it doesn't really matter which one we call the first kind of light and which one we call the second kind of light. Since we've been talking about radio and we've been going to compare the radio to the ultraviolet, I'm just going to have the radio be the E1. So E1 over E2 is frequency 1 over frequency 2. Here is the frequency that we just calculated for the radio wave. And here is the frequency that you're given for the ultraviolet. You plug those in. Notice that the frequencies cancel because we're looking for a ratio, the ratio of one energy to the other energy. And when you have a ratio like that, there will be no units. So if I compare the energy of the radio wave to the energy of the ultraviolet, I get 1.43 times 10 to the negative 6. Or the energy of the radio wave is 1/millionth the energy of the ultraviolet wave. Now let's stop for a second and see if that matches the sniff test. Remember the electromagnetic spectrum. The longer the wavelength, the lower the frequency, the lower the energy. So that is why the red end of the spectrum is much less dangerous than the blue end of the spectrum. Ultraviolet's on the blue end of the spectrum. It has short wavelength and high frequency. Radio is on the other end, the red end, the long wavelength, low frequency, low energy. So does it make sense that a radio wave has only 1/millionth the energy of ultraviolet. You bet it does. Remember that we have to limit our exposure to ultraviolet. Ultraviolet is far more dangerous than radio because it carries far more energy. So it definitely makes sense that the energy of a radio wave is only 1/millionth that of ultraviolet, because we don't have to wear our sunscreen to protect ourselves from radio waves.